So what are we going to do today? We're going to discuss Young's experiment. What's so special about this? So in the previous class, we discussed how we can analyze interference of two identical waves. And today, we're not going to introduce any new physics. We're going to apply exactly the same interference conditions, but now for two lights. So we're going to just discuss interference of visible light. And I will explain why. And what's so special about this particular double slit experiment, right? Again, pretty much no new physics, just we're going to readjust conditions which we derived in the previous lecture for this particular experiment, right? Okay, so let's now start moving. Oh, I need to bring forward my slides. Okay. So before we start discussing that particular experiment, double slit experiment, let's discuss all possible approaches which can be used to model light. Because again, what we do in physics overall, every time we try to model the nature, we're trying to model the nature which was, I don't know, somehow created, I don't know, by God, right? And now we're just trying to use our humble tools, or maybe not so humble, in order to model this, model that, right? And if it works, yeah, we can accept that model, right? Okay, so when we work with light, there are two models which are used. The first one, so whenever you work with a light, so what you have light propagating from the source. Here I have plenty of light sources, and there is some object. So light interacts with the object, right? So usually there are two main players, light and the object. And so now there are two situations. If the size of the object, for example, in this case, maybe it's the diameter of this ball, right? Or radius, it doesn't matter. When the size of the object and wavelength are comparable, it doesn't mean equal. It can be equal, but in general, it can be even, they can be different by a factor of 10 or even 100, right? We can still say they are comparable, right? So if size of the object and wavelengths are comparable, then when they interact around the object, there will be plenty of wave phenomena, some diffraction effects around the object. And if we want to describe them, we need to treat light as a wave. And we need to use what is called wave optics. And that's what we've been using so far, right? And we are going to use that today. So again, if size of an object and wavelengths are comparable, then wave optics must be used. Okay, just a second. Some activity in the chat. Okay, so then, yeah, and in order to sort of demonstrate it, of this, I found this picture, right? I don't remember, from the book, I think. Example with water waves, or waves on water. So we have a screen, you see, black screen with opening of size L. And then there are waves on water propagating towards this opening. And you see the wavelength of this wave. Right. And in this case, we have what is called plane wave. You see these bright lines, they effectively wave fronts. And you see it's basically parallel, straight lines parallel to each other. So how can we get those plane waves, wave fronts like that? You remember in the previous recitation class, in the lecture, we talked about circular waves. And wave fronts were circles, right? So if you let those circles, those wave fronts, propagate for over long distance, then at that point, at those points, right, far, far away, basically at infinity, you're still going to see kind of circles, but circles with such a large radius that for you, they will look like bunch of parallel lines. So that's how you can get wave fronts like this. You just let circular waves propagate to infinity, and you will see bunch of wave fronts looking like this, parallel to each other. So, and that's what is called, this is the example of a plane wave. But anyway, so let's assume that these plane waves hits this opening. And you see what happens after the opening? We have now no longer plane waves, but we have circular waves again. You see they're spreading, right? It's a diffraction effect. Why? Because the size of the opening, basically, that's our object. And wavelengths are comparable. So we have pure wave phenomena, right? And we're going to see a similar situation in our experiment, but of course we're going to use light, right? But here in using example of waves on water, it's a nice example, right? Okay, so it's one situation when wavelengths and size of the object are comparable. We're going to use wave optics. Now the second situation. What if, okay, again I need to bring it forward. Now what if now size of an object is much larger than the wavelength? And this situation we see most of the time in our life, right? Here I have light, right? And it's all visible light, right? So what's the wavelength of light, visible light? It's somewhere between 400 nanometers and 750 nanometers, blue light and red light, right? So pretty much the whole spectrum of visible light. And if you compare that wavelength, 500 nanometers with the size of this object, which is like, 5 centimeters in diameter, this object is gigantic relative to the wavelength of that light, right? And in this case, much better to use what is called array optics, where light is modeled using just basically a bunch of straight lines, which we call arrays, right? In this semester, we wouldn't be able to get to array optics. We're going to stop at wave optics, right? So most of the time in our regular life, people use array optics, right? Because our objects in our everyday life, usually the size of our object significantly larger than the wavelengths of visible light, which we see with our eyes, right? Okay, so these two models of light, and of course we're going to use today still wave optics. Yeah, and if you look at the example with water waves, right? So you see we have plane waves before the opening. Now opening is much larger. The L is much larger than the size of the wavelength. And now we don't see diffraction effect. We have plane waves before and plane waves after the opening, right? Okay, so now to this Young's experiment, double slit experiment, which was done what at the beginning of the 19th century, right? 1801. It's before Napoleon Wars, right? Long back ago. And so what did he do? So he, I took this picture from the book. He took a screen, opaque screen, of course, right? And made two small holes, basically two slits, right? And the sort of the width of those slits is very small, right? This L is small. And he illuminated it with more or less monochromatic light. Now, in these days, of course, it's better, not better. You must use laser light. All right. And so the wavelengths of this light should be comparable to the size of these openings, right? In this direction, right? So to the width of these openings, to the width of these slits. Why do we have to use laser light? Because you remember, again, we're going to use those conditions for interference which we derived in the previous lecture, right? And you remember which waves, traveling waves we used? You remember we had amplitude times sine kx minus omega t plus initial phase. We had omega t, single omega, single frequency, right? Only in that case, if you have monochromatic light, all those conditions which we derived can be used. If you have a light of broad spectrum, then you're not going to observe all these phenomena, right? So you need to use more or less monochromatic source, right, with basically like a single frequency, right? So that's why I told you that, and that's why it is written here, laser beam. It's very important. If you use just a white, okay, just regular light, it is not going to work. Okay, so now, since size of the these openings, the width and wavelengths are comparable, of course, after these slits, we're going to see those diffraction, those like circular waves like we saw in the case of water in the previous slide, right? So now we have this slit creates its own sort of like a circular wave spreading after the screen. And the second slit is going to create the same situation, right? So spreading, light spreading behind the screen, right? And of course, they're going to overlap, right? These two waves artificially created by us, by these two slits. And I claim that they're going to interfere. Why? You remember, in order to observe interference, what do we have to have? Two identical waves. They should have the same amplitude, the same frequency, and the same wavelength, right? And we do have this in this situation, right? Because basically we took the same laser source, laser light, and artificially created out of that light two lights with two openings, with two slits, right? So of course both of these waves have exactly the same properties. They have the same amplitude, they have the same wavelength, and the same period of frequency, right? So of course they're going to interfere, right? And we can use those conditions which we derived in the previous lecture, right? Okay, so now let's look from the top at this picture in order to understand so what's so special about this, because at this point you can tell me, you can start screaming at me, come on, we know how to analyze this interference interference of these two waves, right? You remember in the recitation class when we played with two radio waves, right? You remember we had two antennas, right? Inherent phase difference was basically given, right? In some point, and we were asked to find interference at a certain point, right? So what we did, you measure calculated R1, calculated R2, subtracted, plug it in the condition, right? And then in an attempt to identify, are we going to have constructive or destructive interference? All that can be used here. I can take any point, for example, this point, right? And if I ask you, what are we going to see at that point, constructive or destructive interference? Now you are, as an expert, can say, it's easy, right? Since inherent phase difference must be zero, why zero? Because we just divided the same light into two lights, right? So initial phase will be exactly the same for both of these lights. So the inherent phase difference will be zero, and then you can easily measure, I don't know, R1 from this source, R2 from that source, plug into our interference conditions, and you can easily come up with a conclusion, constructive or destructive interference. So you see, nothing new. But the problem is, this experiment can be used, for example, to measure, I know, the wavelengths or the frequency of unknown light, right? We will actually look at one example, right? Or for some other purposes, right? So what about from experimental point of view? If you want to use this setup to measure something. The trouble is that, yes, all this space will be filled with bright and dark spots, right? Points with constructive and destructive interference. But for our eyes, it's basically invisible, right? Those bright and dark spots. So, of course, you can, for example, try to see those bright and dark spots by now using, I know, fog machine. You can fill this room with, fog, and you can see the bright and dark spots. But from the experimental point of view, it's a lousy setup, really lousy, right? So, what can be done? Again, from the point of view of experimentalist, the easiest solution, again, from the point of view of an experimentalist, if you take a screen, I don't know, white screen, I don't know, piece of paper or something, right? I don't know, white screen, or the wall, and position it at some point, for example, over here, so that you can see those bright and dark spots on the screen. And this will be the best possible setup. Again, from the practical point of view. All right. And so now, then, what do we have to do in this class? We just need to grab those conditions, interference conditions, which we derived in the previous lecture, and readjust them so that we can predict positions of the bright spots on the screen. Again, you see, no new physics. It's just we need to prepare, formulas, set of new conditions, which an experimentalist can use to tell, okay, so my second bright spot will be, at a distance, 5 centimeters from some point on the screen. All right, that's what we want to get. We want to derive a formula which an experimentalist can use in order to use this setup in order to measure some stuff. All right, so that's what I told you. We're not going to introduce new physics. We just need to readjust the formulas which we derived. All right. And before I go, okay, probably let me open this major point. So basically, this is the main idea of today's class, right? In this short explanation. And you know what? Before I go to actually derivation, all right? Look also. How can we determine at which point we're going to have a bright spot and at which point we're going to have dark spot? You remember the problem 1727, I think, right? When we analyzed those overlapping of two circular waves, right? And remember we discussed, so if you have wavefront over wavefront at a certain point, right? So at that point, we're going to have constructive interference, right? Bright spot. And if we have wavefront over sort of a trough, then basically crest over trough, it's a point for destructive interference. Look at this. Along this red line, along this red line, we have bright spots, constructive interference. Why? Because look, we have, if you take, for example, this point, we have wavefront of first wave overlap with wavefront or intersect the wavefront of the second wave. It means that this is the point of constructive interference. Then next, again, wavefront over wavefront, it means that this is constructive interference. Again, wavefront over wavefront, it means crest over crest, constructive interference. Then if you take, for example, this second, you see, straight line, again, it's a line where you're going to see bright spots, because over there, again, you see our intersection of wavefront and wavefront, wavefront and wavefront. As a result, you're going to see another line of bright spots. And of course, between them, between these two red lights, red lines, between these two red lines, you're going to see in the middle what? Overlapping of troughs and crests, right? So you're going to see dark spots, right? Just to explain this picture one more. From slightly different point of view. Okay, so now once we sort of identified the goal, right, the idea, and now let's dive and readjust conditions interference conditions which we derived in the previous lecture. That's simple as that. But the next slide will be kind of messy, but messy from the point of view of geometry usually, right? And we're not going to apply any fancy math. All these steps which I'm going to make, they shouldn't be familiar. You should be familiar with them. They are reasonably simple, right? Okay, so now let's analyze this setup. Okay, experiment. Right. So first, let's bring the system. So we have two slits, right? So this is opaque screen, right? Slit number 1, slit number 2, and of course we need to eliminate this screen with laser light, right? The source must be reasonably monochromatic in order to observe all these phenomena. Okay, then of course we want to see this interference pattern on the screen. So we need to bring the screen. The distance between slits is d, given, right? And the screen where we want to see those bright and dark spots. And of course, we, as an experimentalist, of course, we can position at a certain distance from the double slit, right? Of course, it is usually measured. Let's say L is given. D is also given because it's usually, I don't know, you can buy the double slit system, right? And usually D is labeled. Okay, so DL, and now let's take a completely arbitrary point on the screen, point P, and we want to write conditions, right? Basically readjust conditions at which we're going to see bright spot at this point P. Bright spot, it means constructive interference, right? So we need to write down conditions under which we're going to see constructive interference at that point P. Okay, so now we identified some arbitrary point P, and of course now we need to define its position, right, relative to our system. And first, let's use the angle. So first, let me introduce this auxiliary line, which is basically a center of the double slit, right? So this is the center of double slit, and I just draw this auxiliary line, right? And so we can define position of that spot using angle. This angle, theta. So now I can say that at that angle theta, this point P is, right? Okay, so and now, as I said, we need to readjust our condition, right? And again, we want to get bright spot, conditions for bright spot at that point P. So you remember in the previous class, we derived this, right? 2 pi over lambda times delta r, it's a path length difference, and delta phi naught is the inherent phase difference. And again, you remember we want to get constructive interference at that point. So it must be equal to m times 2 pi. You remember, this is condition for constructive interference. Okay, so now what can we say about, let's start with delta phi naught. I already mentioned it like a few minutes ago about the inherent phase difference. What's the inherent phase difference? It's obviously 0, because we grab basically the same light and split it, creating two fake lights, right? Since the origin of these two lights is the same, right? The same laser light. Of course, they have exactly the same initial phases. So inherent phase difference must be the same. So these two waves, these two sources are in phase, identical sources, right? So delta phi naught is 0. Okay, so if the inherent phase difference is 0, of course we can simplify this condition. And again, we've done it in our previous recitation class, right? Actually, for some of you, no, for everyone, right? You've done it. Right. So if delta phi naught is 0, okay, we can dump this term, and as a result, we can cancel 2 pi over here and 2 pi on the right-hand side. Okay, that 2 pi, right? So 2 pi can be canceled. And wavelength, this wavelength, I can move to the right-hand side of the equation. And as a result, this condition for bright spot will look like this. For the bright spot, constructive interference. Delta R equals m lambda. Again, in the previous recitation class, we use this condition, right? Okay, so that's what we need to use. We just need to write down what now. We figure out what's the story with delta phi naught, and now we need to write down what's the story with delta R. How can we write this path length difference? It's just basically an additional distance that the second wave must to cover on the way to the point, in this case point P, to the point in question, right? Okay, so now I just need to draw R1 and R2 on our diagram, right? Okay, and now I'm drawing it. So I'm drawing it like this. So this will be my R1, right? That direction. And over here, there will be R2. Okay, let me label it. You see R1, and this will be my R2. At this point, you might want to start screaming at me, right? Why? Because what is R1? It's a distance from the source is here, this first slit, to the point in question, to point P, right, which is here. So, of course, strictly speaking, it should be just a straight line from point P to this slit. And I draw kind of line parallel to R2. Again, R2 must be from this slit, right, to point P. But again, I just drew two parallel lines. How come? And of course, that's why I told you at this point you should start screaming at me. So what did I draw? What did I draw? Some strange thing. But you're not wrong, and I'm not completely wrong either. So we both are sort of partially correct. And here's the reason. This picture is not in scale, far from being in scale. Usually, of course, in experimental life, right, this distance to the screen, this L, is, I don't know, several meters. Usually, during the normal semesters, I use demonstration in the lecture class, right? I usually bring the laser, right? So this double slit, and usually we see interference pattern on the wall, right? Usually, the distance to the wall from the double slit, this setup is like 2.5 meters. I usually prepare, right? And typical distance between slits between the slits is about like 0.4, 0.5, 0.3 millimeters, less than a millimeter. 2.5 meters to the screen, and less than a millimeter, less than a half a millimeter, the distance between the slits. So it means that if you draw carefully R1 from this slit to the point on the screen, and from this slit to the point of the screen, you will never be able to see the difference between their directions. For you, they will look like two parallel lines. The difference between this angle theta and this angle, right, which defines direction of this R1 and R2, they will be minuscule, so you wouldn't be able to see. That's why I can, with a very, very good approximation, I basically can draw two parallel lines, R1 representing R1 and representing R2. In order sort of to demonstrate that I took this picture from the book, right? What do we have here? This is the screen, right? This picture is drawn more or less in scale. And over here, we have double slit. It's invisible, right? And this, it looks like a one line, but strictly speaking, it's these two lines, R1 and R2. You will never be able to see the difference in their directions, all right? So with a very good approximation, I can draw them like this, right? So if you wanted to scream at me because it looks like I drew nonsense, you were partially correct, but also I'm not completely wrong, all right? Okay, so this is, and it's all because this picture is not in scale. Right. Okay, let me open the attendance code. So 8446, right? So you have plenty of time to, at some point, enter it. So now, what do we have to do? As I said, we need to find delta R, right? So this R1, this is R2, of course. They all end at point P, right? So delta R is over here. If I draw this line from this slit, perpendicular line from that, oh, I need to bring this PowerPoint forward, all right? Okay. So you see, I just draw a line perpendicular to this R2, right? And this short segment, this one, right? That's our delta R. That's that additional path length that the second wave must to cover on the way to point P. So this is our delta R, which we wanted to find for this condition. So now simple geometry, reasonably simple geometry. First of all, we need to find, you see this, okay, let me open a few, no, let me show that this angle, you see this angle, it's a theta. This angle in this triangle, this point, and this point. You see this triangle? So that angle in that triangle is theta. How come? You see this angle? It's theta, right? And this angle complements this angle to 90 degrees. So if this is theta, this must be 90 minus theta, right? Then again, if I looking at this triangle A, C, B, right? This triangle. So if this is angle 90 minus theta, this angle is 90, then of course this angle must be theta. Right? Again, reasonably simple geometry. So if that angle theta, now we should be able to write expression for this delta R. Again, looking at the triangle, triangle A, B, C, which I just mentioned, right? So this triangle A, B, C, it's a right triangle. So we want to find the side which is opposite to this angle theta. So we know this hypotenuse, which is D, distance between the slits, D sine theta, that's this additional path length, the path length difference, right? So from that triangle ABC, we can write that delta R equals hypotenuse times sine of angle opposite to the side, which is delta R. Okay, so that's what we need. That's what we need, right? So delta R equals d sine theta, and it must be equal to m lambda. So that's constructive interference. So that's the condition that we can use in order to find, in order to see, in order to have a bright spot at point P. So pretty much we can say at this point, okay, goal, we achieved the goal, right? So D is usually given, right? Wavelength is usually also given, right? And this angle theta m will define position of all bright spots. For example, at when m first of all is integer, right? You remember m is integer. When m equals 0, you're going to have a bright spot at the center of the screen. When m equals 0, sine will be also, sine of angle will be 0. Then at angle theta 1, somewhere over here, you're going to have a bright spot number 1. Then at angle theta 2, you're going to have a bright spot number 2. Then at angle theta 3, you're going to have bright spot number 3, and so on. So pretty much this equation allows us to find all angles theta m, which shows us a directions to all those bright spots. Zeroth one, first one, second one, third one, and so on and so forth. Pretty much goal is achieved. But you know what? Once you achieve the goal, what's next natural step of your brain? Your brain starts being creative. in terms of how can I simplify this? How can I make it even a look better, right? Be more practical. So now we are at this point. How can we make this more practical? Okay, I work in optical lab, right? And if you or somebody ask me to use this formula in the experimental setup, measuring angles, I will not be happy. And I'm sure that you will experience the same feelings. Why? Because measuring angle, especially when, yeah, you don't see the light, of course you need to somehow sample it, right? It's not very practical, right? It's, again, I wouldn't like it. Because it's not very convenient to measure angles. It's better, or much better, to measure, for example, distances. For example, you can just grab the ruler, position it next to the screen, right? And measure, for example, the distance from the center of the screen to the point where, for example, the bright spot number 2 is, or bright spot number 3 is. It's better to measure distance on the screen than measure angles to find positions of those bright spots. Much easier to measure the distances. I doubt that you disagree with me, right? Again, from the experimental point of view. So now, again, we basically you can use this if you if you like this, right? But it's better to slightly adjust it and measure angles. Measure distances, right? Measure distances, right, from the center of the screen. So let's introduce our coordinate system now, right? So, as I said, let's replace theta with some y, which defines position of the bright spot relative to the center of the screen. So let me introduce coordinate system. Vertical, you see, y-axis goes up, right? So this is y. And of course, the origin is at the center of the screen. Y equals 0. Then, of course, this will be y1, this will be y2, right? This will be y3, and so on. And if this is our bright spot number n, of course, this will be y sub, okay, m, not n, m, sorry. So this will be y sub m. So now, how can we make a transition from this angle theta to this y sub m? Piece of cake. Just the right triangle. Look at this triangle. Point S, you see, I just opened point S. Point P and point O. It's a right triangle. SPO. If you look at the triangle, how can we find this distance ym? You take tangent of this angle, since it's a right triangle, it will be a ratio of opposite side versus adjacent side. Adjacent side, we know it's a length, distance to the screen, L. So tangent theta equals to ym divided by L, right? So that's the equation which can be used to make a transition from measuring angles to measuring distances along the screen. As simple as that. You see, just a simple properties of a right triangle. So now we can use the first condition, right? I just rewrote it over here, right? D sine theta equals m lambda. And the first equation just allows us to make a transition from the angles to distances. So these two equations can be used. But it's not over in terms of simplifications. We can make one small step further. Deeper, right, in order to simplify these equations one more time. Again, usually during the regular semester, I usually bring the experimental setup, right, and we usually see those bright fringes, right? And it's obvious when you see the experiment that these angles, these thetas, are very, very small. Very small. All right. If angles are small, what can be used? Taylor expansions. And you already used it at the very beginning of the semester. You remember one of the problems where you had to use Taylor expansions. And according to them, tangent of, okay, let's start with sine. Sine of angle is approximately equal to the angle, but of course the angle must be in radians. It's a Taylor expansion. And tangent of the angle must be equal to the angle itself. Again, just a Taylor expansions. And so now, as a result, we can combine these two equations, because instead of tangent theta, I can write theta, and instead of sine of theta, I can write theta. So we can combine these equations through the theta. So theta, it will be ym over L equals to m lambda divided by d, right? So that's what I have. And again, what we want to solve it for ym, which can be used to find the position of the bright spots relative to the center. So ym will be equal to m lambda over m lambda L divided by d. So finally, this is the final formula which we usually use if double slit experiment is used. So which allows us to find positions of bright spots, okay, visible on the screen, right, from the center of the screen. M is an integer, 0, 1, 2, 3, 4, 5, all the way to infinity, right? Because we're going to see many bright spots. Lambda, wavelength. L is the distance to the screen. Usually it's measured experimentally. And D, again, it's not a big deal. You can measure the distance between the slits, right? Okay, so that's the condition. You see, it's a little bit messy. But again, in terms of mathematics or geometry, it's not that complicated. And for your level, but of course, you have to make several steps together in nice sequence. Right? Okay, so at the end of the day, you just need to use this formula, nothing else. So the problems are much simpler than the derivation. Right? But I didn't feel like just presenting this formula because it's just out of nowhere. All right, it's not something fundamental. Right? Okay, so now, yeah, of course. And of course, relative to the center of the screen, we have a symmetry. Here's the bright spot corresponding. Okay, first of all, at the center of the screen, there must be bright spot all the time. It doesn't matter which light you use. At the center, there will be bright spot. Then, bright spot corresponding to m equals 1, bright spot corresponding to m equals 1. You see the symmetry. Then, m equals 2, and again, m equals 2 on that side. M equals 3, m equals 3. So we have a symmetry relative to the center of the screen. Complete symmetry, of course, expected. Right? It shouldn't be surprised. You shouldn't be surprised. Okay, so now, of course, very similar. You can write for dark fringes, but usually these formulas are not used because you know dark fringes, dark spots between two adjacent bright spots, right? So in the middle, there will be dark spots. So usually the formulas from the previous slide is enough. Okay, so now additional interesting feature. You can easily find the distance between bright fringes. If you take the distance to the bright spot m plus 1 and bright spot m, basically two adjacent bright spots, and subtract their distances, right? Distances to them, you will get like this. I just use the formula which I just derived. So it's a m plus 1 lambda L over d minus m lambda L over d. Of course, this m with lambda L over d and this last term gets cancelled, and we have just lambda L divided by d. So it means what? Since it doesn't depend on m, it means all bright spots are equally spaced. The distances between bright spots exactly the same. It doesn't matter if you use 99th one and 100th one, or between distance between the first one and the second one. They're equally spaced. Right? So distances between all these bright fringes are going to be the same. All right. Okay. All right. It's enough now. Let me look at one example, one problem. I was planning to ask you a clicker question, but it looks like we are getting closer to the end of the class. Let me look at the example. So we're going to skip this conceptual question. Right. So let me switch to the whiteboard. So, chapter 33, problem 1. So what do we have here? There is a double slit. This is slit number 1, slit number 2. Then there is a screen. Here is L, but it's not given. L is not given. Distance between slits also is not given. Right? And we have two lights hitting this double slit simultaneously. Orange light, lambda sub OR, and the wavelength of that orange light is given 600 nanometers. And then there is an unknown light. Again, you must use some monochromatic lights, right? Something produced by lasers, right? Okay, so we have two lights shining on the same double slit. And of course, there will be two interference patterns created on the screen. First one is created by the orange light, right? And the second one is created by the unknown light. Then additional piece of information is given. It was observed, because you see those blue interference pattern and red one. Okay, not a red, orange one, right? And it was observed that fourth bright spot of an unknown light overlaps with the third bright spot of an orange light. So there is an overlapping over here. You see here it's a mess, but overlapping at these fringes. So based on this information, we should be able to find the wavelengths of an unknown light. It's sort of a simple version, limited in applicability, a spectrometer. Simple version of a spectrometer. Okay, what do you usually do with spectrometer? Measure the frequency or the wavelengths of an unknown light. That's what we want to do here, right? But of course, it's very limited in terms of applications, right? Okay, so now what can we do? Not much. We just know that the bright spot of what? Unknown light. Okay, you know what? Which way I wrote it? Okay, subscript. Okay. So we know that the fourth bright spot of an unknown light equals to position of the third bright spot of an orange light, right? So, okay, let me show on the diagram also. So what is y4 sub x? It's this, y sub 4 upper script x, right? And what is this? It's this distance, y sub 3 of an orange light. You remember this y's define position of bright spots relative to the center. And the formula which we just derived, y sub m equals m lambda times L divided by D. L is the distance to the screen. D, it's the distance between the slits, right? So we can apply this formula. Okay, let me sort of frame it. It's a sort of like a fundamental formula for this problem, right? So we just need to apply it for this and that and equate them, because we know that these two bright spots overlap. Okay, now let me write it underneath. So unknown light. So this will be 4. Then lambda of an unknown light, lambda x. Then, since both of the lights illuminate the same system, so L is exactly the same for both lights. So I'm going to use the same L for both of these Y's, right? And then D is the same, right? Because this interference pattern is created by the same double slit. So distance D is the same for both orange and an unknown light. So divided by the same D. And this is what now? M equals 3. It's I'm working with the orange. Lambda orange times the same L and divided by the same D, right? Okay, so L can be, of course, cancelled because it's the same for both. D can be cancelled, it's the same. And what's left? 4 lambda x equals to 3 lambda orange. Of course, we can solve it for lambda x. And we will get 3/4 of orange wavelength. Of course, if you plug numbers, 3/4 over 600 nanometers you will end up with lambda x equals to 450, I think, yeah, 450 nanometers. You see, application is easier, but of course derivation was a little bit kind of lengthy, but in terms of complexity, not that complicated. Okay, so there is another problem will be in my slides, right? This problem and another problem. You can look at that. It's slightly more complicated, but again, it's all about this formula, right? All about this formula. Okay, class. Oh, yeah, I mean, okay, guys, right. So the class is over, and the lectures are over, right, this semester.